I've just shown you that the form of trace formulas, resolve, and determinants propagates into the theory where we have symmetries. This is very minor modification. Instead of prime orbits that close once in a full state space, we have relative prime orbits that close on themselves. Fundamental domain, or in reduced, symmetry-reduced space in case of continuous systems. The determinants, spectral determinants, because evolution operator is a linear operator working on some function space which describes how density of trajectories evolve and how they're correlated. This one factorizes because it's a linear theory, and this determinant becomes a product of determinants. Here comes something that your professor doesn't know. Because in this theory we have a very direct duality between evolution of densities or functions defined on a state space versus microscopic information, recurrent motion on the state space, so periodic orbits, classical trajectories on space of finite dimension usually. We have formulas which I call cycle expansions, and they have very interesting structure under group symmetry which is not at all intuitive. Department of True Admissions, what we did is we first noted that structure, and then we had to learn the theory of discrete groups. We never wanted to learn the theory of discrete groups, but we first discovered that periodic orbits actually factorize in a totally non-obvious way. And then we had to develop theory which turned out to be known since the 19th century that explains it. So you've been taught the correct thing, but that's not how science works. You first discover some amazing result which you can't understand, and then you find by Googling or otherwise some theory. So when you look at cycle expansions, and for pedagogical reasons I'll only do zeta functions, but everything is also true for the full theory of spectral determinants. What we found is that if we can determine zeros of dynamical zeta function, then the only thing we have to do is we have to compute the weight of every prime orbit. And the weight of every prime orbit is very intuitive. It's a product of its expanding eigenvalues in this formulation of the theory. And then I pay penalty for long cycles. And I'm interested in making predictions, so I compute my observable on one repeat of the prime cycle. This theory turned out to be nice, convergent theory. One can argue that as I include longer and longer period orbits, I'm getting exponentially improved answers for them. And that basically has to do with these two factors, that we expect stability in hyperbolic systems to be growing exponentially with length of the orbit. And we pay the penalty for long orbits as well. This is totally general, but now with symmetry. The way we got to this is we were looking at the traces, but now the traces have extra part in them. There is a part that has to do with the regular representation and the position of how far relative prime orbit has advanced in a big state space. Repeated r times. And then there was the deterministic evolution opera, which this time I'll write out explicitly, which had two pieces. One is we always start in the fundamental domain with a point on the orbit. But then we advanced just a prime orbit away. And we had sums of repeats. So to close the cycle, I either do it once or r times. And then I land someplace, but I have to bring that point back. And that I do by the matrix representation of the action of the group on the state space by going r times with this. And now you have this extra weight, originally just identity, but if you write as sum of irreducible representation, then you get contributions which are not just for returning orbit, but for other values of this group parameter. And you work a little bit, it's not very hard, and what you find is that this expression on the left-hand side can be now written as a product if you have an orbit in a fundamental domain, then it has some number of copies in a big space. So for example, if your orbit just stayed within fundamental tile, then in a big space there'll be 6 copies of it because it could start in any other tile. If it's hopping between the two tiles, then there might be 3 copies of it because it can do it 3 ways. So that's the multiplicity in a big space. Your prime orbit, relative prime orbit, has to be shorter than your full orbit. So it cares about the multiplicity. So if it's a periodic orbit, both in your reduced space and in the tile and in a full space, then multiplicity will be 6, and it'll be just the same thing. But if it's half of the orbit, then multiplicity will be 3, and this factor will be 2. This just means I have to go twice along the relative periodic orbit to close the full orbit. So at this level, this is just an identity. This is the same formula, just written in terms of weights of prime orbits. Nothing has happened. But then this thing happens. It's written as a sum of irreducible representations. And now this trace has a name for irreducible. It's a character of irreducible representation. And the moment this happens, there is a new set of formulas. And now if you go through the steps that we had before, because the evolution operator is now a matrix times this function within a tile, then that matrix, by the time I get back to the dynamical zeta function is a version of a spectral determinant. And as I'm summing up traces, I'll actually produce a determinant, the usual relation between determinants. So once I've used these Irreps, I get a new formula which is much less obvious than the original one. It says that this is a determinant of 1 minus. Now this is, for 3D, this is 6-dimensional matrix. So this is this relation I already used here. Under symmetry reduction, this determinant, the zeta function, becomes a product of determinants, one for each irreducible representation. And remember, for 3-disk problem, we had only 3 irreducible representations, so it won't be such a big deal to work it out. But weighted with the character of the group representations. But before I get there, because there's still a determinant, this is not quite a character yet. This is the action of the group irreducible representation. So for example, for 3 disks, we had 1 plus 1, and then we had 2 times 2-dimensional representation. So there'll be 2-dimensional matrix here yet. But I'll show you how you evaluate in terms of characters next. The zeta function explicitly multiplies, and so does Fredholm determinant for a process in the 1 for each irreducible representation. And they are all easier to compute than the original ones. They're only computed on the fundamental domain. And it turns out that the convergence of computational spectrum is greatly enhanced. So before I go to a specific example, let me just tell you why the convergence gets better. Why do you care about that?
You will not be able to stay home, brother. You will not be able to plug in, turn on, and cop out. You will not be able to lose yourself on